So we already have one technique available to us for solving an exponential equation. We can rewrite both sides in terms of the same base, where that's possible. Now that's possible in this example. 4 to the x plus 1 equals 8. We can rewrite it as 4 is 2 squared, 8 is 2 to the third. And so this equation becomes 2 squared to the x plus 1 equals 2 to the third. Since those expressions are equal and they have the same base, the exponents must also be equal. Power of a power rule says we multiply these exponents together. 2 times x plus 1 equals, this exponent on the right is 3. Distribute on the left. 2x plus 2 is 3. Subtract 2 from both sides, and 2x is 1. Divide both sides by 2, and x is 1/2. So that was the basic method that we learned when we first met exponential expressions. We now have another method using the log. And we can think of this method in two ways. We can think of it as taking the log base 4 of both sides, choosing base 4 because that's the base of my exponential. And then we can think, well, the log base 4 of 4 to the something is just the something. Or we can think the log and the exponential cancel out. And on the left we get x plus 1. And on the right we get log 4 of 8. But we've already seen the move that takes us directly from here to here. And we call that rewriting in log form. So we can make that move directly, just rewriting the equation. We don't need to write the step where we take the log of both sides, because all we're doing is rephrasing this in terms of an inverse instead of in terms of the original function. Either way, we then get that x is -1 plus the log base 4 of 8, which we can put into our calculator as the log of 8 over the log of 4. And when we do that, we'll say -1 plus the log of 8 over the log of 4. And we get 1/2 again. So either way we get the same solution. X equals 1/2. Now the nice thing about this method where we use the logs is that we can do the same thing even when we don't have a way to rewrite for method 1. That is, even if we can't rewrite each side using the same base, we can still use the method using logs. Let's see how that works out in this example. We have 3 to the power x minus 5 equals 29. And so we can, as our very first move, rewrite this as x minus 5 equals the log base 3 of 29. Add 5 to both sides, and that gives us x equals 5 plus the log base 3 of 29. Or, in terms of the common log, 5 plus the log of 29 over the log of 3. In the last example, good things happened to us when we threw that into the calculator. Let's see what happens if we throw this one into the calculator. We'll say 5 plus the log of 29 over the log of 3. We get some nasty decimal. This calculator loves giving us fractions. If it could make this a fraction, it would. It can't. So how can we give this answer? There are 2 possible ways to give this answer. One, we can give the exact solution. So when we say give the exact solution, we mean don't throw it into your calculator and get a decimal. Just write down the expression that gives it to you in the simplest possible form. And this is giving us slightly more specific instructions in terms of the common log. So that means give this expression. The reason that we give that kind of exact solution, just like when we were solving quadratics, is because we don't know what level of precision we're going to need. We can later on calculate that to whatever level of precision we need for whatever our actual goal is. The other way we could give this answer is as a decimal approximation, so taking that number on the calculator and rounding it. Usually our instructions would include how many decimal places to round it to. But an example of a decimal approximation of this might be rounded to 2 decimal places, 8.07. So 8.07 is the solution to 2 decimal places. And we can even check that solution by taking 3 to the power 8.07 minus 5 and confirming that we really do get something very close to 29. Which form should you give your solution in? In math class, whichever the instructions say to do. In real life, whatever you actually need for your application. In general, in real life, you'll get a decimal or fractional approximation, and how precise it is going to depend on what you're trying to accomplish. Now, the other thing to be aware of when solving exponential equations is that just like any other function, we need to isolate the exponential before we apply the inverse. So how does that work? Here I have this equation where the variable is in this exponential function. So I'm going to start by getting rid of the 6. I have a half times my exponential expression plus 6 is 24. I'll subtract 6 from both sides and get a half times my exponential expression is 18. Multiply both sides by 2 to get rid of that half, and I get that my exponential expression equals 36. One common mistake I see at this point is to forget that we have 3 to the power something and pretend that that's 3 times something and divide by 3. Dividing by 3 will not help us here, right? Dividing by 3 would just change that exponent. It's not helpful. What we need at this point is a log. We need to rewrite this in log form. So we rewrite this as 2x minus 1, our exponent, equals the log base 3 of 36. And now we finish solving for x. So we have 2x is 1 plus the log base 3 of 36. And then we divide by 2, and we get x is 1/2 plus 1/2 of the log base 3 of 36. Now, if we felt like it, we could use log rules to mess around with this. But we don't have to. If we want to give an exact answer, we have x equals 1/2 plus, well, we'll have a half times the log of 36 over the log of 3. So we can actually get rid of that 1, right? We don't need that extra 1 in the numerator. Or if we wanted to get a decimal approximation, we could throw that into the calculator. We have a half plus log 36 over 2 log 3, and we get that that's about 2.131. And we can check that by plugging it in. If we take a half times 3 to the, well, we'll have 2 times our value of x, 2.131, minus 1, and then get out of the exponent and say plus 6, we get something very close to 24, as we'd hoped. And that's about as complicated as it gets for solving equations with one exponential. In the next video, we'll see what to do if we have more than one exponential expression in the same equation.